All right, today we're going to look at some kind of different data structures for static trees. So we have, at least in the second two problems, we have a static tree. We want to pre-process it to answer lots of queries. And all the queries we're going to support today we'll do in constant time per operation, which is pretty awesome, and linear space. That's our goal. It's going to be hard to achieve these goals, but in the end we will do it for all three of these problems. So let me tell you about these problems. Range minimum queries. You're given an array of numbers and the kind of query you want to support, we'll call RMQ of ij, is to find the minimum in a range. So we have AI up to AJ. And we want to compute the minimum in that range. So I and J form the query. I think it's pretty clear what this means. I give you an interval that I care about, IJ. I want to know in this range what's the smallest value. And a little more subtle, this will come up later, I don't just want to know the value that's there, like say this is the minimum among that shaded region, but I also want to know the index k between I and j of that element. Of course, if I know the index, I can also look up the value. So it's more interesting to know that index. Okay, this is a non-tree problem, but it will be closely related to a tree problem, namely LCA. So LCA problem is you want to pre-process a tree, say a rooted tree, and the query is LCA of two nodes, which I think you know, or I guess I call them X and Y. So it has two nodes, X and Y, in the tree. I want to find their lowest common ancestor, which looks something like that. At some point they have shared ancestors, and we want to find that lowest one. And then another problem we're going to solve is level ancestor, which again, pre-process a rooted tree. And the query is a little different. Given a node and an integer k, positive integer, I want to find the kth ancestor of that node, which you might write parent to the k, meaning I have a node x, the first ancestor is its parent. Eventually I want to get to the kth ancestor, so I want to jump from x to there. So it's like teleporting to a target height above me. Obviously, k cannot be larger than the depth of the node. So these are the three problems we're going to solve today: RMQ, LCA, and LA. Using somewhat similar techniques, we're going to use a nice technique called table lookup, which is generally useful for a lot of data structures. We are working in the word RAM throughout. But it's not as essential as it has been in our past integer data structures. Now, the fun thing about these problems is while LCA and LA look quite similar, I mean, they even share two letters out of three, they're quite different. As far as I know, you need fairly different techniques to deal with, or as far as anyone knows, you need pretty different techniques to deal with both of them. The original paper that solved level ancestors kind of lamented on this. RMQ, on the other hand, turns out to be basically identical to LCA. So that's the more surprising thing, and I want to start with that. Again, our goal is to get constant time linear space for all these problems. Constant time is easy to get with polynomial space. You could just store all the answers. There's only n squared different queries for all these problems. So quadratic space is easy. Linear space is the hard part. So let me tell you about a nice reduction from an array to a tree. very simple idea. It's called the Cartesian tree. It goes back to Gabot, Bentley, and Tarja in 1984. So it's an old idea, but it comes up now and then, and in particular provides the equivalence between RMQ and LCA, or one direction of it. I just take a minimum element, let's call it AI, of the array. Let that be the root of my tree, and then the left subtree of T is just going to be a Cartesian tree on all the elements to the left of I. So A less than I. And then the right subtree is going to be A greater than I. So let's do a little example. Suppose we have 8, 7, 2, 8, 6, 9, 4, 5. So the minimum in this array is 2, so it gets promoted to the root, which decomposes the problem into two halves, the left half and the right half. So drawing the tree, I put 2, maybe over here is actually nicer. 2 at the root. On the left side, 7 is the smallest, and so it's going to get promoted to be the root. And so the left side will look like this. On the right side, the minimum is 4. So 4 is the right root, which decomposes into left half there, the right half there. So the right thing is just 5. Here the minimum is 6, and so we get a nice binary tree on the left here. Okay, this is not a binary search tree, it's a min heap. Right. Cartesian tree is a min heap. But Cartesian trees have a more interesting property, which I've kind of alluded to a couple times already, which is that LCAs in this tree correspond to RMQs in this array. Okay, so let's do some examples. Let's say I do LCA of 7 and 8. That's 2. Anything from the left and the right subtree, the LCA is 2. And indeed, if I take any interval that spans 2, then the RMQ is 2. If I don't span 2, I'm either in the left or in the right. Let's say I'm on the right. Say I do an LCA between 9 and 5, I get 4, because, yeah, the RMQ between 9 and 5 is 4. Make sense? Same problem, really. Because it's all about which mins, in the sequence of mins, which mins do you contain? If you contain the first min you contain, the highest min you contain, that is the answer. And that's what LCA in this tree gives you. So LCA of I and j in this tree T equals RMQ in the original array of the corresponding elements. So there's a bijection between these items, and so I and j here represents nodes in here corresponding to the corresponding items in A. Okay, so this says if you wanted to solve RMQ, you can reduce it to an LCA problem. Quick note here, which is, there's a couple different versions of Cartesian trees when you have ties. So here I only had 1, 2. If there was another 2, then you could either just break ties arbitrarily and you get a binary tree, or you could make them all one node, which is kind of messier, and then you get a non-binary tree. I think I'll say we disambiguate arbitrarily, just pick any min, and then you get a binary tree. It won't affect the answer. Although I think the original paper might do it a different way. Okay. Let's see. So then let me just mention a fun fact about this reduction, which is that you can compute it in linear time. This is a fun fact we basically saw last class, although in a completely different setting, so it's not at all obvious. But you may recall we had a method last time for building a compressed trie in linear time. Basically, the same thing works here, although it seems quite different. The idea is if you want to build this, if you build a Cartesian tree according to this recursive algorithm, you will spend n log n time, or actually maybe even quadratic time, if you're computing min with a linear scan. So don't use that recursive algorithm. Just walk through the array left to right one at a time. So first you insert 8, then you insert 7. You realize, oh, 7 would have won, so you put 7 above 8. Then you insert 2. You say, oh, that's even higher than 7, so I'll have to put it up here. Then you insert 8, so that you'll just go down from there, and you put 8 as the right child of 2. Then you insert 6. You say, whoops, 6 actually would have gone in between 2 and 8. And the way you'd see that is, I mean, at that moment, your tree looks something like this. You've got 2, 8, and there's other stuff to the left, but I don't actually care. I just care about the right spine. Say, oh, I'm inserting 6. 6 would have been above 8, but not above 2. Therefore, it fits along this edge. And so I convert this tree into this pattern, and it will always look like this. 8 becomes a child of 7. Sorry, 6. 6. Thanks. Not 7. 7 was on the left. This is the guy I'm inserting next because here. So, I mean, it doesn't, there's no, well, I guess it's a left child because it's the first one. So we insert 6 like this. So now the new right spine is 2, 6. And from then on, we will always be working to the right of that. We'll never be touching any of this left stuff. Okay, so how long did it take me to do that? In general, I have a right spine of the tree, which are all right edges. And I might have to walk up several steps before I discover, whoops, this is where the next item belongs. And then I convert it into this new entry, which has a left child, which is that stuff. But this stuff becomes irrelevant from then on, because now this is the new right spine. And so if this is a long walk, I charge that to the decrease in the length of the right spine, just like that algorithm last time. Slightly different notion of right spine. So same amortization, you get linear time, and you can build the Cartesian tree. This is actually where that algorithm comes from. This one was first, I believe. Any questions? So this is, I mean, I'm not worrying too much about build time, how long it takes to build these data structures, but they can all be built in linear time. And this is one of the cooler algorithms, and it's a nice tie-in to last lecture. So that's a reduction from RMQ to LCA. So now all of our problems are about trees in some sense. But I mean, there's a reason I mentioned RMQ, not just that it's a handy problem to have solved, but we're actually going to use RMQ to solve LCA. So we're going to go back and forth between the two a lot. Actually, we'll spend most of our time in RMQ land. So let me tell you about the reverse direction. If you want to reduce LCA to RMQ, that also works. And you can kind of see it in this picture. If I gave you this tree, how would you reconstruct this array? Pop quiz. How do I go from here to here? In order traversal. Yep. Just do an in order traversal, write those guys down. I mean, yeah. Pretty easy. Now, not so easy because in the LCA problem, I don't have numbers in the nodes. So if I do an in order walk and I write stuff, it's like, what should I write for each of the nodes? Any suggestions? The height, not quite the height, the depth. That will work. So let's do it just so it's clear. Take the same tree. Is that the same tree? Yep. So write the depths. 0, 1, 1, 2, 2, 2, 3, 3. It's either height or depth, and you try them both. This is depth. So I do an in-order walk. I get 2, 1, 0. So I can't even read my writing. 3, 2, 3, 1, 2. It's funny doing an in-order traversal in something that's not a binary search tree, but there it is. That's the order in which you visit the nodes. And you stare at it long enough, this sequence will behave exactly the same as this sequence. Of course, not in terms of the actual values returned, but if you do the argmin version of RMQ, you just ask for what's the index that gives me the min. If you can solve RMQ on this structure, then that argmin RMQ will give you exactly the same answers as this structure, which is kind of nifty. Because here I had numbers, they could be all over the place. Here I have very clean numbers. They will go between 0 and the height of the tree. So in general, at most, 0 to n minus 1. So a fun consequence of this is you get a tool for universe reduction in RMQ. The tree problems don't have this issue because they don't involve numbers, they involve trees. And that's why this reduction does this. But you can start from an arbitrary ordered universe and have an RMQ problem on that, and you can convert it to LCA, and then you can convert it to a nice clean universe RMQ. Just by doing the Cartesian tree and then doing the in-order traversal of the depths. This is kind of nifty because if you look at these algorithms, they only assume a comparison model. So these don't have to be numbers, they just have to be something from a totally ordered universe that you can compare in constant time. You do this reduction, and now we can assume they are integers, nice small integers, and that will let us solve things in constant time using the word RAM. So you don't need to assume that about the original values. Cool. So, time to actually solve something. We've done reductions. We now know RMQ and LCA are equivalent. Let's solve them both. Kind of like the last the sorting we saw, there's going to be a lot of steps. They're not sequential steps. These are like different versions of a data structure for solving RMQ, and they're going to be getting progressively better and better. So LCA, which implies RMQ. This was originally solved by Harrell and Tarjan in 1984, but is rather complicated. And then what I'm going to talk about is a version from 2000 by Bender and Farch Colton, same authors from the cache oblivious B trees. That's a much simpler presentation. So, first step is I want to do this reduction again from LCA to RMQ, but slightly differently. And we're going to get a more restricted problem called plus or minus 1 RMQ. What is plus or minus 1 RMQ? Just means that you get an array where all adjacent values differ by plus or minus 1. Okay, if you look at the numbers here, a lot of them differ by plus or minus 1. These all do. But then there's some big gaps, like this has a gap of 3, this has a gap of 2. This is plus or minus 1. That's almost right. And if you just stare at this idea of tree walk enough, you'll realize a little trick to make the array a little bit bigger, but give you plus or minus 1s. If you've done a lot of tree traversal, this will come quite naturally. This is a depth first search. This is how the depth first search order of visiting a tree in order. This is usually called an Eulerian tour, a concept we'll come back to in a few lectures. But Euler tour just means you visit every edge twice, in this case. And so if you look at the node visits, I'm visiting this node here, here, and here, 3 times. But it's amortized constant because every edge is just visited twice. Okay, what I'd like to do is follow an Euler tour and then write down all the nodes that I visit, but with repetition. So in that picture, I will get 0, 1, 2, 1. That's, I go 0, 1, 2, back to 1, back to 0, then over to the 1 on the right, then to the 2, then to the 3, then back up to the 2, then down to the other 3, then back up to the 2, back up to the 1, back down to the last node on the right, then back up and back up. Okay, this is what we call the Euler tour. So with multiple visits, for example, here's all the places that the root is visited. Here's all the places that this node is visited. Then this node is visited 3 times. It's going to be visited once per incident edge. Okay, I think you get the pattern. I'm just going to store this. And what else am I going to do? Let's see. Each node in the tree stores, let's say, the first visit in the array. Pretty sure this is enough. You could maybe store the last visit as well. We can only store a constant number of things. And I guess each array item stores a pointer to the corresponding node in the tree. Okay, so each instance of the 0 stores a pointer to the root, and so on. Which is kind of what these horizontal bars are indicating, but those aren't actually stored. Okay, so I claim still RMQ in here is the same as LCA over there. It's maybe a little more subtle, but now if I want to compute the LCA of 2 nodes, I look at their first occurrences. So let's do, I don't know, 2 and 3. Here, this 2 and this 3, and I didn't label them, but I happen to know where they are. 2 is here, and it's the first 3. So now here, they happen to only occur once in the tour, so it's a little clearer. If I compute the RMQ, I get this 0, as opposed to the other zeros, but this 0 points to the root, so I get the LCA. Let's do ones that do not have unique occurrences. So like this guy and this guy, the first 1 and the first 2. That would be this one and this one. So in fact, I think any of the 2s would work. It doesn't really matter. Just have to pick one of them. So I picked the leftmost one for consistency. Then I take the RMQ. Again, I get 0. You can test that for all of them. I think the slightly more subtle case is when one node is an ancestor of another. So let's do that. 1 here and 3 there. Here you have to be, I think here you do need to be leftmost or rightmost consistently. So I take the 1 and I take the second 3. Okay, I take the RMQ of that, I get 1, which is the higher of the 2. Okay, so it seems to work. Actually, I think it would work no matter which guy you pick. I just pick the first one. Okay, no big deal. And you're not going to see why this is useful for a little bit until step 4 or something, but we've slightly simplified our problem to this plus or minus 1 RMQ. Otherwise, identical to this in-order traversal. So not a big deal, but we'll need it later. Okay. That was a reduction. Next, we're finally going to actually solve something. I'm going to do constant time n log n space RMQ. This data structure will not require plus or minus 1 RMQ. It works for any RMQ. It's actually a very simple idea. And it's almost what we need, but we're going to have to get rid of this log factor. That will be step 3. Okay, so here's the idea. You've got an array. And now someone gives you an arbitrary interval from here to here. Ideally, I just store the mins for every possible interval, but there's n squared intervals. So instead, what I'm going to do is store the answer, not for all the intervals, but for all intervals of length the power of 2. Trick you've probably seen before. So this is the easy thing to do, and then the interesting thing is how you make it actually get down to linear space. Length power of 2. Okay, there are only log n possible powers of 2. There's still n different start points for those intervals. So total number of intervals is n log n. So this is n log n space because I'm storing an index for each of them. Okay, and then if I have an arbitrary query, the point is, let's call it length k, then I can cover it by 2 intervals of length a power of 2. They will be the same length. They will be length 2 to the floor of log k, the next smaller power of 2 below k. Maybe k is a power of 2, in which case it's just 1 interval or 2 equal intervals. But in general, you just take the next smaller power of 2. That will cover more than half of the thing, of the interval. And so you have one that's left aligned, one that's right aligned. Together, those will cover everything. And because the min operation has this nifty feature that you can take the min of all these, take the min of the 2, you will get the min overall. It doesn't hurt to have duplicate entries. That's kind of important. Property of min. It holds for other properties too, like max, but not everything. Then, boom, we've solved RMQ. Okay, I think it's clear. You do 2 queries, take the min of the 2. Actually, you have to restore the argmin, so it's a little more work, but constant time. Cool. That was easy. Maybe I'll leave LCA up there. Okay, so we're almost there, right? Just a log factor off. So what technique do we have for shaving log factors? Indirection. Yeah, our good friend indirection. Indirection comes to our rescue yet again, but we won't be done. The idea is, well, we want to remove a log factor before we've removed log factors from time, but there's no real time here, right? Everything's constant time. But we can use indirection to shave a log factor in space, too. Let's just divide. So this is, again, for RMQ. So I have an array. I'm going to divide the array into groups of size, I believe, half log n. Would be the right magic number. It's going to be theta log n, but I need a specific constant for step 4. So what does that mean? Well, I have the first half log n entries in the array. Then I have the next half log n entries. And then I have the last half log n entries. Okay, that's easy enough. But now I'd like to tie all of these structures together. A natural way to do that is with a big structure on top of size n over log n. I guess with a factor 2 out here. N over half log n. How do I do that? Well, this is an RMQ problem, so a natural thing to do is just take the min of everything here. So the red here is going to denote taking the min. And take that, the one item that results by taking the min in that group, and promoting it to the next level. This is a static thing we do ahead of time. Now, if I'm given a query, like say this interval, what I need to do is first compute the min in this range within a bottom structure. Maybe also compute the min within this range, the last bottom structure. And then these guys are all taken in entirety, so I can just take the corresponding interval up here, and that will give me simultaneously the mins of everything below. So now a query is going to be the min of 2 bottoms and 1 top. In other words, I do one top RMQ query for everything strictly between the 2 ends. Then I do a bottom query for the one end, a bottom query for the other end. Take the min of all those values, and really it's the argmin. But clear? So it would be constant time if I can do bottom in constant time, if I can do top in constant time. But the big win is that this top structure only has to store n over log n items. So I can afford an n log n space data structure because the logs cancel. So I'm going to use structure 2 for the top. That will give me constant time up here, linear space. So all that's left is to solve the bottoms individually. Again, similar kind of structure to Van M. DeBose. We have a summary structure and we have the details down below, but the parameters are way out of whack. It's no longer root n, root n. Now these guys are super tiny because we only needed this to be a little bit smaller than n, and then this would work out to linear space. Okay, so step 4 is going to be how do we solve the bottom structures? So step 4, this is where we're going to use technique of lookup tables. For bottom groups. This is going to be slightly weird to phrase because on the one hand I want to be thinking about an individual group, but my solution is actually going to solve all groups simultaneously, and it's kind of important. But for now, let's just think of one group. So it has size n prime, and n prime is half log n. I need to remember how it relates to the original value of n so I know how to pay for things. The idea is there's really not many different problems of size half log n. And here's where we're going to use the fact that we are in plus or minus 1 land. Okay, we have this giant string of integers. And now we're looking at log n of them and say, okay, this is the sequence 0, 1, 2, 3. Over here as 0, 1, 2, 1. There's all these different things. Then there's other things like 2, 3, 2, 3. There's a couple annoying things. One is it matters what value you start at, maybe, and then it matters what the sequence of plus and minus 1s are after that. Okay? I claim it doesn't really matter what value you start at because RMQ, this query, is invariant under adding some value x to all entries, all values in the array. Right? If I add 100 to every value, then the minimums stay the same in position. So again, I'm thinking of RMQ as an argmin, so it's giving just the index of where it lives. So in particular, I'm going to add minus the first value of the array to all values. I should probably call this, well, yeah. Here I'm just thinking about a single group for now. So in a single group, saying, well, it starts at some value. I'm just going to decrease all of these things by whatever that value is. Now some of them might become negative, but at least now we start with a 0. So what we start with is irrelevant. What remains, the remaining numbers here are completely defined by the gaps between, or the diffs between consecutive items. And the diffs are all plus or minus 1. So now the number of possible arrays in a group, so in a single group, is equal to the number of plus or minus 1 strings of length n prime, which is half log n. And the number of plus or minus 1 strings of length n prime is 2 to the n prime. So we get 2 to the half log n, also known as square root of n. Square root of n is small. We're aiming for a linear space. This means that for not only for every group, there's n over log n groups, but actually many of the groups have to be the same. There's n over log n groups, but there's only root n different types of groups. So on average, like root n over log n occurrences of each. So we can kind of compress things down and say, hey, I would like to just store a lookup table for each one of these, but that would be quadratic space. But there's really only square root of n different types. So if I use a layer of indirection, I guess, different sort of indirection, if I just have, for each of these groups, I just store a pointer to the type of group, which is what the plus or minus 1 string is. And then for that type, I store a lookup table of all possibilities. That will be efficient. Let me show that to you. This is a very handy idea. In general, when you have something of size log, if you have a lot of things of size roughly log n, lookup tables are a good idea. And this naturally arises when you're using indirection, because usually you just need to shave a log or two. So here we have these different types. So what we're going to do is store a lookup table that says for each group type, well, I'll just say a lookup table of all answers. Do that for each group type. Group type meaning the plus or minus one string. It's really what is in that group after you do the shifting. Okay, now there's square root of n group types. What does it take to store the answers? Well, there's, I guess, half log n squared different queries, because n prime is half log n, and a query is defined by the two endpoints. So there's at most this many queries. Each query, to store the answer, is going to take order log n bits. This is if you're fancy, because the answer is an index into that array of size half log n. So you need log n bits to write down that. So the total size of this lookup table is the product of these things. We have to write root n lookup tables. Each has size, stores log squared n different values, and the values require log n bits. And so total number of bits is this thing, and this thing is little o of n. So smaller than linear, so it's irrelevant. You can store it for free. Now, if we have a bottom group, the one thing we need to do is store a pointer from that bottom group to the corresponding section of the lookup table for that group type. So each group stores a pointer. Let's say into lookup table. I'm of two minds whether I think of this as a single lookup table that's parameterized first by group type and then by the query. So it's like a two-dimensional table or three-dimensional, depending how you count. Or you can think of there being several lookup tables, one for each group type, and then you're pointing to a single lookup table. However you want to think about it, same thing. Same difference, as they say. This gives us linear space. These pointers take linear space. The top structure takes linear space, linear number of words. And constant query time, because lookup tables are very fast. You just look into them. They give you the answer. So you can do a lookup table here, and then over here you do the covering by two powers of two intervals. Again, we have a lookup table for those intervals. So it's like we're looking into four tables, take the min of them all, done. That is RMQ and also LCA. Actually, it was really LCA that we solved, because we needed this. We solved plus or minus one RMQ, which solved LCA, but by the Cartesian tree reduction, that also solves RMQ. So now we solved 2 out of 3 of our problems. Any questions? Good. Still have lots. Level ancestors are going to be harder, a little bit harder. Similar number of steps. I'd say they're a little more clever. This is kind of what this I feel is pretty easy. Very simple style of indirection, very simple style of enumeration here. It's going to be a little more sophisticated and a little bit more representative of the general case for level ancestors. Definitely fancier. Level ancestors is a similar story. It was solved a while ago, but it was kind of complicated solution, and then Bender and Farch-Colton found it and said, hey, we can simplify this, and I'm going to give you the simplified version. So this is level ancestors. So it was originally solved by Berkman and Vishkin in 1994. Okay, not so long ago. And then the new version is from 2004. Ready? Level ancestors. What was the problem again? Here it is. I give you a rooted tree. give you a node and a level that I want to go up, and then I level up by k. So I go to the kth ancestor, or parent to the k. This may seem superficially like LCA, but it's very different. I mean, because as you can see, RMQ was very specific to LCA. It's not going to let you solve level ancestors in any sense. I don't think. Maybe you could try to do the Cartesian tree reduction, but solution we'll see is completely different, although similar in spirit. So, step 1. This one's going to be a little bit less obvious that we will succeed. Okay, here we started with n log n space. It's just shaving a log, no big deal. Here I'm going to give you a couple of strategies that aren't even constant time. They're log time, or worse. And yet you combine them and you get constant time. It's crazy. Again, each of the pieces is going to be pretty intuitive, not super surprising. But it's one of these things where you take all these ingredients that are all kind of obvious, you stare at them for a while like, oh, I put them together and it works. It's like magic. All right, so first goal is going to be n log n space log n query. So here's a way to do it with the technique called jump pointers. In this case, nodes are going to have log n different pointers, and they're going to point to the 2 to the ith ancestor for all I. I guess the maximum possible I would be log n. You can never go up more than n. So, I mean, ideally, you'd have a pointer to all your ancestors. Then in an array, boom, in quadratic space, you solve your problem in constant time. But it's a little more interesting. Now every node only has pointers to log n different places. So it's looking like this. This is the ancestor path. So n log n space. And I claim with this you can roughly do a binary search if you wanted to. Now, we're not actually going to use this query algorithm for anything, but I'll write it down just so it feels like we've accomplished something, namely log n query time. So, what do? I set x to be the 2 to the floor log kth ancestor of x. Okay, remember, we're given a node x and a value k that we want to rise by. So I take the power of 2 just below k. That's 2 to the floor log k. I go up that much. And that's my new x, and then I set k to be k minus that value. That's how much I have left to go. Okay, this thing will be less than k over 2, right? Because I mean, the next previous power of 2 is bigger than half of the thing. So we got more than halfway there, and so after log n iterations, we'll actually get there. Okay, that's pretty easy. That's jump pointers. Two logs that we need to get rid of. And yes, we will use indirection, but not yet. First, we need some more ingredients. This next ingredient is kind of funny because it will seem useless, but in fact, it is useful as a step towards ingredient 3. So our next trick is called long path decomposition. In general, this class covers a lot of different tree decompositions. We did preferred path decomposition for Tango trees. We're going to do long path now. We'll do another one called heavy path later. There's a lot of them out there. This one won't seem very useful at first because while it will achieve linear space, it will achieve the amazing square root of n query, which I guess is new. I mean, we don't know how to do that yet with linear space. Not so obvious how to get root n, but anyway, don't worry about the query time. It's more the concept of long path that's interesting. It's a step in the right direction. So here's how we're going to decompose a tree. First thing we do is find the longest root to leaf path in the tree. Okay, so if you look at a tree, it has some wavy bottom. Take the deepest node. Take the path, the unique path from the root to that node. Okay? When I do that, I could imagine deleting those nodes. Or there's that path, and then there's everything else, which means there's all these triangles hanging off of that path. Some on the left, some on the right. Actually, I haven't talked about this, but both LCA and level ancestors work not just for binary trees, they work for arbitrary trees. And somewhere along here, here, this reduction of using the Euler tour works for non-binary trees too. That's actually another reason why this reduction is better than in-order traversal by itself. In-order traversal works only for binary trees. This thing works for any tree. In that case, in an arbitrary tree, you visit the node many, many times, potentially. Okay, but it'll still be linear space, and everything will still work. Here also, I want to handle non-binary trees. So I'm going to draw things hanging off, but in fact, there might be several things hanging off here, each their own little tree. Okay, but the point is, here's my red. Here. There was this one path in the beginning, the longest path, and then there's stuff hanging off of it. So just recurse in all the things hanging off of it. Recursively decompose those subtrees. Okay. Not clear what this is going to give you. In fact, it's not going to be so awesome, but it will be a starting point. Now, you can answer a query with this as follows. Query. Oh, sorry, I should say how we're actually storing these paths. Here's the cool idea with this path thing. Okay, I have this path. I'd like to be able to jump around on at least, suppose your tree was a path. Suppose your tree were a path. Then what would you want to do? Store the nodes in an array ordered by depth. Because then if you're at position I and you need to go to position I minus k, boom, that's just a lookup into your array. So I'm going to store each path as an array. As an array of nodes, or node pointers, I guess, ordered by depth. So if it happens, if my query value x is somewhere on this path, and if this path encompasses where I need to go, so if I need to go k up and I end up here, then that's instantaneous. The trouble would be is if I have a query, let's say, over here, and so there's going to be a path that guy lives on, but maybe the kth ancestor is not on that path, it could be on a higher up path. Okay, it could be on the red path, and I can't jump there instantaneously. Nonetheless, there is a decent query algorithm here. All right. So here's what we're going to do. If k is less than or equal to the index I of node x on its path, so every node belongs to exactly one path. This is a path decomposition. It's a partition of the tree into paths. Not all the edges are represented, but all the nodes are there. All the nodes belong to some path. And so, and we're going to store, for every node, store what its index is and where it lives in its array. Okay, so look at that index in the array. If k is less than or equal to that index, then we can solve our problem instantly by looking at the path array at position I minus k. That's what I said before. If our kth ancestor is within the path, then that's where it will be. And that's going to work as long as that is non-negative. When I get to negative, that means it's another path. Okay, so that's the good case. The other case is we're just going to do some recursion, essentially. So we're going to go as high as we can with this path. We're going to look at path array at position 0. Go to the parent of that. Let's suppose every node has a parent pointer. That's easy. Regular tree. And then decrease k by 1 plus I. Okay, so the array let us jump up I steps. That's this part. And then the parent stepped us up one more step. That's just to get to the next path above us. Okay, so how much did this decrease k by? I'd like to say a factor of 2 and get log n, but in fact, no, it's not very good. It doesn't decrease k by very much. It does decrease k, guaranteed by at least 1. So it's definitely linear time. And there's a bad tree, which is this. It's like a grid. Whoa, sorry. Okay, here's a tree. It's a binary tree. And if you set it up right, this is the longest path. And then when you decompose, this is the longest path, and this is the longest path, this is the longest path. If you query here, you'll walk up to here, and then walk up to here, and walk up to here, and walk up to here. So this is a square root of n lower bound for this algorithm. So not a good algorithm yet, but the makings of a good algorithm. Makings of step 3, which is called ladder decomposition. Ladder decomposition is something I haven't really seen anywhere else. I think it comes from the parallel algorithms world in general. And now we're going to achieve linear space log n query. Now this is an improvement. So we have at the moment n log n space log n query or n space root n query. We're basically taking the min of the two. Right, so we're getting linear space log n query. Still not perfect. We want constant query. That's when we'll use indirection, I think. Yeah, basically. A new type of indirection, but okay, so linear space log n query. Well, the idea is just to fix long paths. And it's a crazy idea. Okay, let me tell you the idea, and then it's like, why would that be useful? But it's obvious that it doesn't hurt you. Okay, when we have these paths, sometimes they're long, sometimes they're not long enough. Just take each of these paths and extend them upwards by a factor of 2. That's the idea. Extend, so take number 2, extend each path upward 2x. So that gives us, call a ladder. Okay, what happens? Well, paths are going to overlap. Fine. Ladders overlap. The original paths don't overlap. Ladders overlap. I don't really care if they overlap. How much space is there? It's still linear space because I'm just doubling everything. So at most doubled space relative to long path decomposition. I didn't mention it explicitly, but long path decomposition is linear space. We're just partitioning up the tree into little pieces. Doesn't take much. We have to store those arrays, but every node appears in exactly one cell here. Now every node will appear in, on average, 2 cells in some weird way. Like, what happens over here? I have no idea. So this guy's length 1. It's going to grow to length 2. This one's length 2, so now it'll grow to length 4. This one's length 3. I mean, it depends how you count. I'm counting nodes here. So it's going to go here all the way to the top. Interesting. And all the others will go to the top. So if I'm here, I walk here, then I can jump all the way to the top, then I can jump all the way to the root. Not totally obvious, but it actually will be log n steps. Let's prove that. It's, again, something we don't really need to know for the final solution, but kind of nice, kind of comforting to know that we've gotten down to log n query. So it's at most double the space. So still linear. Now, there's one catch. Over in this world, we said each, I didn't say it, but I meant to, or I mentioned it out loud. Every node stores what array it lives in. Now a node lives in multiple arrays. Okay, so which one do I store a pointer to? Well, there's one obvious one to store a pointer to. There's whatever node you take lives in one path. In the long path decomposition, it still lives in one path. Store a pointer into that ladder. Okay, so node stores a pointer. You could say to the ladder that contains it in the lower half. That corresponds to the one where it was an actual path. And only one ladder will contain a node in its lower half. The upper half was the extension. I guess it's like those folding ladders you extend. Okay? Cool. So that's what we're going to do, and also store its index in the array. Now we can do exactly this query algorithm, again, except now instead of path it says ladder. So you look at the index of the node in its ladder. If that index is larger than k, then boom, that ladder array will tell you exactly where to go. Otherwise, you go to the top of the ladder, and then you take the parent pointer, and you decrease by this. But now I claim that decrease will be substantial. Why? If I have a node of height h, remember height of a node is the length of the longest path from there downward, it will be on a ladder of height at least 2h. Why? Because if you look at a node of height h, like say, I don't know, this node, it lives, the longest path from there is, substantial. I mean, if it's height h, then the longest path from there is length at least h. So every node of height h will be on a path of length at least h, and from there down. And so you look at the ladder, well, that's going to be double that. So the ladder will be height at least 2h, which means if your query starts at height h, after you do one step of this ladder search, you will get to height at least 2h, and then 4h, and then 8h. And you're increasing your height by a factor of 2 every time. So in log n steps, you will get to wherever you need to go. Okay, you don't have to worry about overshooting, because that's the case when the array tells you exactly where to go. Okay. Time for the climax. This won't be the end, but it's the climax in the middle of the story. So we have, on the one hand, jump pointers. Remember those? Jump pointers made small steps initially and got... actually, no, they made this is what it looks like for the data structure. But if you look at the algorithm, actually it makes a big step in the beginning. Right? It gets more than halfway there. Then it makes smaller and smaller steps, exponentially decreasing steps. Finally, it arrives at the intended node. Ladder decomposition is doing the reverse. If you start at low height, you're going to make very small steps in the beginning. As your height gets bigger, you're going to be making bigger and bigger steps. And then when you jump over your node, you found it instantly. So it's kind of the opposite of jump pointers. So what we're going to do is take jump pointers and add them to ladder decomposition. This is, I guess, version 4. Combine jump pointers from 1 and ladders from 3. Forget about 2. 2 is just a warm-up for 3. Long paths, defined ladders. Okay, so we've got one way to do log n query. We've got another way to do log n query. I combine them, and I get constant query. Because log n plus log n equals 1? I don't know. Yeah. Okay. here's the idea. On the one hand, jump pointers make a big step and then smaller steps, or, like that. And on the other hand, ladders make small steps. Oh, it's hard to draw. Okay. What I'd like to do is take this step and this step. That would be good. Only two of them. So query is going to do one jump plus one ladder in that order. See, the thing about ladders is it's really slow in the beginning because your height is small. I really want to get large height. Jump pointers give you large height. The very first step, you get almost half the height you need. That's it. So when we do a jump, we will we do one step of the jump algorithm. What do? We reach height at least k over 2 above x. Right? We get halfway there. So our height is a little let's say x has height h. Okay, so then we get to height, this is saying we get to height h plus k over 2. Okay, so that's good. This is a big height. Halfway there. Halfway of the remainder after h. Now ladders double your height in every step. So ladder step, so this is the jump step. If you do one ladder step, you will reach height double that. So it's at least 2h plus k, which is bigger than what we need. We need h plus k. That's where we're trying to go. And so we're done. Isn't that cool? So this first step gets you, so the annoying part is, there's this extra part here. This is the h part. That's, we start at some level. We don't know where. This is x. The worst case is maybe when it's very small, but whatever it is, we do this step. This is our target up here. This is height h plus k. In one step, we get more than halfway there with the jump pointer, and then the ladder will carry us the rest of the way. Because this is a ladder. We basically go horizontally to fall on this ladder, and it will cover us beyond where we need to go, beyond our wildest imaginations. So this is k over 2. Because not only will it double this, which is what we need to double, it will also double whatever's down here, this h part. So it gets us way beyond where we need to go. It could be h is 0, then it gets us to exactly where we need to go. But then the ladder tells us where to go. So 2 steps, constant time. Now, one annoying thing is we're not done with space. So this is the anticlimax part. It's still going to be pretty interesting. We've got to shave off a log factor in space. But hey, we're experienced. We already did that once today. Question?
Why is it okay to go past your target?
So it's okay. So jump pointer, the question was, why is it okay to go past our target? Jump pointers aren't allowed because they only know how to go up. They can't overshoot. That's why they went less than halfway. Or more than halfway, but less than the full way. Ladder decomposition can go beyond. Because the point is, as soon as here's you, x, and here's your kth ancestor, this is the answer. As soon as you're in a common ladder, then the array tells you where to go. So even though the top of the ladder overshot, there will be a ladder connecting you to that top of the ladder. So as long as it's somewhere in between, it's free. Yeah, so that's why it's okay. This goes potentially too high. So it's good for ladders, not good for jumps. But that's exactly where we have it. Other questions? Yeah.
Wouldn't you be high up enough in the tree so that just long path would work?
Oh, interesting question. So would it be enough to do jump pointers plus long path? My guess is no. So jump pointers get you up to, so think of the case where h is 0. Initially you're at height 0. I think that's going to be a problem. You jump up to height k over 2 with a jump pointer. Now in long path decomposition, you know that the path will have at length at least k over 2, but you need to get up to k. And so you may get stuck in this kind of situation where maybe you're trying to get to the root and you jump to here, but then you have to walk So I think the long paths aren't enough. You need that factor of 2, which the ladders give you. You can see where ladders come from now, right? I mean, we got up to height k over 2. Now we just need to double it. Hey, we can afford to double every path, but I think we need to. Other questions? Okay. So last thing to do is to shave off this log factor of space. And we're going to do that with indirection, of course. Constant time and log n space. But it's not our usual type of indirection. Use this board. Indirection. So last time we did indirection, it was with an array. And that's actually pretty much every indirection we've done, it's been with an array-like thing. We could decompose into groups of size log n, and the top thing was n over log n. So it's kind of clean. This structure is not so clean because it's a tree. How do you decompose a tree into little things at the bottom of size log n and the top thing of size n over log n? Suppose, for example, your tree is a path. Ooh, bad news. Bad news. My tree were a path. Well, I could trim off bottom thing of size log n, but now the rest is of size n minus log n, not n divided by log n. That's bad. I need to shave a factor of log n, not an additive log n. Can you tell me a good thing about a path? I mean, obviously, when we can put it in an array, but can you quantify the goodness or the path-likedness of a tree? Well, I erase this board. It's kind of a vague question, but. Good thing about a path is that it doesn't have very many leaves. That's one way to quantify pathedness. If a small number of leaves, I claim life's not so bad. I actually need to do that before we get to indirection. Step 5 is let's tune jump pointers a bit. I want to make them so they're the problem, right? That's where we get n log n space. They're the only source of our n log n space. So what I'd like to do is in this situation where the number of leaves is small, we'll see what small is in a moment, I would like jump pointers to be linear size. Okay, here's the idea. First idea is let's just store jump pointers from leaves. Okay, so that would imply L log n space, I guess, plus linear overall. Instead of n log n, now we just pay for the leaves. Except we kind of messed up our query. First thing query did was at the node follow a jump pointer. But it's not so bad. Here we are at x. There's some leaves down here. And we want to jump up from here, from x. How do I jump up from x? Well, if I could somehow go from x to really any leaf, the ancestors of x that I care about are also ancestors of any leaf descendant of x. So all I need to do is store for each node any leaf descendant. Single pointer. This will be linear. From every node. Okay? So I start at x. I jump down to an arbitrary leaf, say this one. And now, so I have to do a query. Jump down. and let's say I jump down by d, then my k becomes k plus d, right? If I went down by d, then and I want to go up by k from my original point, now I have to go up by k plus d. But hey, it's just, I mean, we know how to go up from any node that has jump pointers. So now we have a new node, a leaf. So it has a jump pointer, has jump pointers upward. So we follow that one jump pointer to get us halfway there from our new starting point. We follow one ladder thing, and we can get to the level ancestor k plus d from the leaf, and that's the level ancestor k from x. Okay, this is like a reduction to the leaf situation. We really don't have to support queries from arbitrary nodes. Just go down to a leaf and then solve the problem from the leaf. Okay? Okay, so now if the number of leaves is small, my space will get small. How small does L have to be? N divided by log n. Interesting. If I could get the top structure to not have n over log n nodes, that's not possible. I can at best get to n minus log n nodes. If I could get it down to n over log n leaves, that would be enough to make this linear space. And indeed, I can. This is a technique called tree trimming, or I call it that. I don't know if anyone else does. But I think I've called it that in enough papers that we're allowed to call it that. So, boom. It's originally invented by Alstrup and others for a particular data structure. There's many versions of it. We will see other versions in future lectures, but here's the version you need for this problem. Okay, here's the plan. I have a tree. And I want to identify all the maximally deep nodes that have at least log n nodes below them. This will seem weird because we really care about leaves and so on. So, there's stuff hanging off here, whatever. I guess I'm thinking of that as one big tree. No, actually, I'm not. Okay, I do need to separate these out. But one of these nodes could have arbitrarily many children. We have no idea. It's an arbitrary tree. Okay, and what I know is that each of these triangles has size less than quarter log n, because otherwise this node was not maximally deep. Okay, so if this head size is greater than or equal to quarter log n, then that would have been the node where I cut, not this one. So I'm circling the nodes that I cut below, so meaning I cut these edges. Okay, so these things have size less than a quarter log n, but these nodes have at least a quarter log n nodes below them. So how many of these circled nodes are there? Well, at most 4 n over log n such nodes. Right? Because I can charge this node to at least a quarter log n nodes that disappear in the top structure. So if there's at most now, but these things become the leaves. Right? If I cut all the edges going down from there, that makes it a leaf. And they're the only leaves. They're the only leaves? Yeah. I mean, if you look at a leaf, then it has size less than a quarter log n. So you will cut above it somewhere. So every old leaf will be down here. And the only new leaves will be the cut nodes. Okay, so we have order n over log n. Leaves. Yes. Good. So it's funny. We're cutting according to counting nodes, descendants, not leaves. Won't work if you cut with leaves. Cut with nodes, but then the thing that we care about is the number of leaves went down. That will be enough. Great. So up here, we can afford to use 5, the tuned jump pointer combined with ladder structure. Because this only costs L log n. L is now n over log n, so the log n's cancel. So linear space to store the jump pointers from these circled nodes. So if our query is anywhere up here, then we go to a descendant leaf in the top structure, and we can go wherever we need to go. If our query is in one of the little trees at the bottom, which are small, they're only 1/4 log n, so we're going to use a lookup table. Either our answer is inside the triangle, in which case we really need to query that structure, or it's up here. If it's up here, we just need to know, basically, if every node down here stores a pointer to the dot above it, then we can first go there, see is that too high? If it's too high, then our answer is in here. If it's not too high, then we just do the corresponding query in structure 5. Okay, so the last remaining thing is to solve a query that stays entirely within a triangle, a bottom structure. And that's where we use lookup tables. Again, things are going to be similar to last time, except we're now up to step 7. But it's a little bit messier because instead of arrays, we have trees. And here it's like we graduate from baby combinatorics, which is how many plus or minus 1 strings there are, power 2, to how many trees are there. Anyone know how many trees on n nodes there are? It's a one-word answer. No. Nice. That is a correct one-word answer. Very good. Not the one I had in mind, but anyone else? Nope. You're thinking n to the n. That would be bad. We could not afford that because log n to the log n is super polynomial. Fortunately, it's not that big. It's roughly 4 to the n. The correct answer, the exact answer is called the nth Catalan number, which didn't tell you much. I didn't write it down, but I'm pretty sure it is 2n prime, choose n prime, 1 over n prime plus 1-ish. Don't quote me on that. It's roughly that. It might be exactly that. Someone with the internet can check. But it is at most 4 to the n prime. So that the computer science answer is 4 to the n, indeed. It's just some asymptotics here. Why is it 4 to the n? 4 to the n you could also write as 2 to the 2n prime, which is, first let's check this is good, and then I'll explain why this is true in a computer science way. So we've got 1/4 log n up here. So the 1, 2 cancels with 1, 2 up here. So we have 2 to the half log n. So this is our good friend root n. Root n is just something that's n to the something, but is n to the something less than 1. So we can afford some log factors. Why are there only 2 to the 2n prime trees? One way to see that is you can encode a tree using 2n bits. If I have an n-node tree, I can encode it with 2n bits. How? Do an Euler tour. And all you really need to know from an Euler tour to reconstruct the tree is, at each step, did I go down or did I go up? Those are the only things you can do. If you went down, it's to a new child. If you went up, it's to an old node. So if I told you a sequence of bits, for every step in the Euler tour, did I go down or did I go up, you can reconstruct the tree. Now, how many bits do I have to do? Well, twice the number of edges in the tree, because the length of an Euler tour is twice the number of edges in the tree. So 2n bits are enough to encode any tree. That's the computer science information theoretic way to prove it. You could also do it from this formula, but then you'd have to know why the formula is correct, and that's messier. Cool. So we're almost done. We have root n possible different structures down here. We've got n over log n of them, or maybe. I don't know. It's a little harder to know exactly how many of them there are, but I don't care. There's only root n different types, and so I only need to store a lookup table for each type. The number of queries is, order log squared n again, because our structures are of size order log n. And the answer to a query is, again, order log n bits, because there's only log n different nodes to point to. And so the total space is order root n log n squared log n for the lookup table. And then each of these triangles stores a pointer, or I guess every node in here stores a pointer to what tree we're in, or what type of tree we have, and also what node in that tree we are in. So every guy in here, because that's now part of the query, has to store not only a little bit more specific pointer into this table. It actually tells you what the query part is, or the first part of the query, the node x. Then the table also is parameterized by k. So one of these logs is which node you're querying. The other log is now the value k, but again, you'd never go up higher than log n. If you went up higher than log n, then you'd be in the 5 structure. And so you just do a query up there. You don't need a query in the bottom. OK, so there's only that many queries. And so space for this lookup table is little of n again. And so we're dominated by the space for these pointers and for the space up here, which is linear. So linear space, constant query. Boom. Any questions? I have an open question. Maybe. I think it's open. What if you wanted to do dynamic? 30 seconds of dynamic. For LCA, it's known how to do dynamic LCA with constant operations. The operations are add a leaf. You can add another leaf. Given an edge, subdivide that edge into that. And also the reverse. So I can erase a guy, put the edge back, delete a leaf, those sorts of things. Those operations can all be done in constant time for LCA. What about level ancestor? I have no idea. Maybe we'll work on it today. That's it.